Welcome to this session. In this session, we are going to briefly discuss on design of infinite impulse response filter. Which is simply called as IIR filter. Let us have a small discussion on the previous sessions. Let us consider a continuous time linear time invariant system whose input is x of t and output is y of t, assuming the impulse response of the system as h of t. X of t is the input signal, y of t is the output signal, and h of t is the impulse response of the system. And these three functions are related to each other with the help of mathematical relation y of t equals x of t convolution with h of t. Assuming this as equation number 1. Taking Laplace transform of equation 1, we shall get y of s equals x of s multiplied with h of s, where h of s is the transfer function of the system. H of s is represented by the Laplace transform of output over the Laplace transform of input at zero initial conditions. Let us assuming that this transfer function consists of n number of poles and m number of zeros. H of s may be represented by the numerator polynomial of order m and the denominator polynomial of order n. Which can be simply represented by y of s over x of s. So this term will be simply represented as Assuming this as equation number 2 and taking inverse Laplace transform of equation 2, we shall get summation of m equal to 0 to m bm d power m y of t divided by dt power m, which will be equal to summation of n equal to 0 to n an d power n x of t divided by dt power n. So let us consider this equation as number 3, and 3 is called as the differential equation governing the LTI system. And the poles and zeros are represented in the S-plane, and here our intention is to design the digital infinite impulse response filter. Here the representation is given in analog filter, so this analog filter has to be converted into digital filter. The design specifications of analog filters are converted into design specifications of digital filters, and the conversion is only valid and effective if the system is linear time invariant system and it, it is a stable system. As we speak about the stable system, all of its poles should lie in the left half of the S-plane. So the conversion of analog filter into digital filter is done with the help of two methods. There are two methods are involved in this process. One is impulse invariance transform method, and another one is bilinear transformation method. Let us discuss the first method, which is called as impulse invariance transform method. The name itself is having some meaning, in which the impulse response of the digital filter is obtained by uniformly sampling the impulse response of the filter, of the analog filter. Here, the impulse response of the digital filter h of n is obtained by sampling the impulse response of the analog filter h of t. That means if the transfer function of the analog linear time invariant filter is known, assuming that h of s as the transfer function of analog linear time invariant system is given by taking inverse Laplace transform of h of s, we shall get h of t, which is called as impulse response of analog filter. And this h of t is uniformly sampled at the sampling rate of fs with the sampling period of ts that means at every time instant nts, where ts is the sampling period. We shall get the impulse response of the digital filter. And after that, if you take z transform of h of n, we may get h of z, which is the transfer function of digital IIR filter. This is how the impulse invariance transform method converts the analog filter into digital filter. Here, the samples are taken from the impulse response of the analog LTI filter at every time instance NTS. We can get the impulse response of the digital filter. Here there are two transforms are used. In analog domain, the Laplace transform is used, and in digital domain, the Z transform is used. So we should remember the Laplace transform of different functions. Remember that Laplace transform of the unit step function is 1 by s, and e power at u of t is 1 divided by s minus a, and e power minus at u of t is 1 divided by s plus a. Similarly, the Z transform of several functions are represented by the Z transform of the unit step discrete time function is represented as and the Z transform of a power n u of n as 1 over 1 minus a into z power minus 1. So we should recall all these transfer functions. So now let us assume an IIR filter whose analog transfer function is having only one pole. So h of s can be represented as 1 divided by s minus p1. Let us assume that p1 is the pole which is located on the right half of the s-plane. If suppose the pole is located, suppose the denominator consists of the polynomial function s1 divided by s plus pi, then it represents the left half pole, which means s is equal to minus pi. So now we need to take inverse Laplace transform of this transfer function, which will provide h of t. h of t equals e to the power minus p1t u of t. And now the impulse invariance transform method samples this function to convert this impulse response of the analog filter into impulse response of the digital filter. So this will be represented as we are sampling the time instant at nts. So this equation will now become h of n equals e power minus p1 tsn multiplied by u of n. And now this is the impulse response of digital filter. The impulse response of the digital filter is transformed into Z domain which we can get h of z as 1 over 1 minus e power minus p1 ts into z to the power minus 1. So this is the transfer function of the infinite impulse response filter. So If there is any function in the transfer function of the analog filter is represented by 1 over s plus pi, it can be simply replaced by the function of IIR, digital IIR filter, that is 1 over 1 minus e to the power minus p1 ts z to the power minus 1, where ts is the sampling time duration, where ts is the sampling duration. Similarly, the impulse invariance transform method converts the pole locations from S plane to Z plane using the following configurations. If the system has distinct poles, that means if the system has distinct poles S plus 1 divided by S plus Pi, where the pole is located at minus Pi, then this transfer function can be, the part of the transfer function can be 1 over 1 minus e to the power minus Pi Ts z to the power minus 1, as we already discussed. Consecutively, if the system transfer function has multiple poles at the same location in the S-plane, say, for example, the transfer function consists of the terms 1 over s plus pi to the power m, which means that the m number of poles are located in the left half of the S-plane at the coordinate minus pi, then that function can be replaced by the equivalent digital IIR representation using impulse invariant transformation method is represented as minus 1 to the power of m minus 1 over m minus 1 factorial d power m minus 1 by dpi to the power m minus 1 of the function, that is the m minus 1th derivative of the function with respect to pi of the function 1 over 1 minus e to the power minus pi ts z to the power minus 1. Similarly, if the system consists of complex poles, which means that the system transfer function consists of complex poles, that is S plus A divided by S plus A the whole square plus B square. This part of the transfer function of the analog filter is transformed into and the another form of transfer function can be represented as here it is important to note that the mapping of S-plane, the poles in the S-plane to the Z-plane. We know that S is represented by sigma plus j omega and Z is represented by R into e power j omega. Here sigma decides the location of the poles, whether it should be lying on the left half of the S-plane or lying on the right half of the S-plane. So sigma decides the stability of the pole, and omega is the analog frequency measured in radians per second, and here omega is represented by digital frequency, which is also a measure of radians per second. And we know that Z is equal to e to the power st. And if this equation is expressed as e to the power sigma plus j omega t, and the z can be represented as r into e to the power j omega, so this equation can be finally written as r e power j omega equals e power sigma t multiplied by e power j omega t. That means the magnitude of this equation r is equal to e power sigma t. Similarly, the phase angle of this equation can be represented by small omega equals omega t. That means omega ts. So in all part of the t, we have to represent ts because ts is the sampling duration. So here there may be three possibilities. If sigma is less than, that is, let us discuss three different cases. Case 1, that is if sigma is less than 0. If sigma is less than 0, R will become e power minus sigma ts, so that R will be represented as 1 divided by e power sigma ts, which means that R is always less than 1. And case 2, if sigma equal to 0, that means R equal to e power 0, which will be equal to 1. So the value of R equals 1. Case 3, if sigma is greater than 1, that means sigma is a positive value, R equal to e power sigma ts, that means R is greater than 1. With these three cases, we represent the poles on S plane and the poles on the Z plane. In such a way, the mapping of poles on the S plane is done. So let us consider these three different cases with the help of let us consider the S plane and the Z plane. So if sigma is negative, that is sigma is less than 0, case 1. If sigma is less than 0, that is case 1, the poles are located on the left part of the S plane. Then this will be mapped. Here the case 1 represents the R should be less than 1. So the R is equal to 1 is represented by a circle whose radius is unity. It is having the dimension of 1 on all the axes. So the poles on the left half of the S plane is mapped inside the unit circle. Now let us discuss the second case, case 2. That is if sigma equal to 0. So this is sigma equal to 0 line, that is imaginary axis of the S plane. If any poles lying on this imaginary axis is represented in the Z plane in such a way that in case 2 we discussed as if sigma equal to 0, the value of R equals 1. Hence these poles are represented on the poles on the imaginary axis are represented on the unit circle in the z plane. And let us assume the case 3 where sigma is a positive value, that is sigma greater than 0. In this case, if sigma is greater than 0, then R is greater than 1. So any poles located on the right half of the S plane, then that are all represented in the Z plane in such a way that outside the unit circle, the poles are mapped onto the Z plane outside the unit circle. So this is how the mapping of poles and zeros on the S plane to the Z plane can be done. And here we have represented three cases. Either the poles may be having only one value, one distinct value, or multiple poles can be located on the same locations. So the multiple poles on the S plane are mapped onto the single location of the Z plane. This kind of mapping is called as many to one mapping. In the next class, we shall briefly discuss about the bilinear transformation method. And here we need to assume that the location of the mapping of the S plane poles and zeros to the Z plane with respect to magnitude is clearly explained, and we know that the digital frequency omega is always directly proportional to the analog frequency omega, and which are all linearly represented by omega is equal to omega ts, where ts is the sampling duration. Here ts is representing the proportionality constant. So the analog frequency omega can be represented as digital frequency omega over ts.